Hello everyone, welcome to our final lecture of the course on Python for data science. In this lecture, we'll conclude our Capstone project on predicting the price of pre-owned cars by comparing linear regression and random forest regression models. Before we dive in, let's take a quick recap of what we covered in our last session. We started by addressing missing values, removing duplicates, and dropping unnecessary columns. We derived a new variable to accurately capture the age of each car using the year and month of registration. We explored the distributions of key numerical variables like price, power, age, and kilometer using histograms and box plots to identify and understand outliers. We calculated the correlation matrix to understand the relationships between the numerical variables and identified power as the most influential variable affecting the price. By refining our dataset and understanding these relationships, we've set a solid foundation for building our regression model. Today, we'll be focusing on creating and evaluating different regression models, starting with a simple linear regression and then exploring more complex models like random forest regressor. We'll split our data into training and testing sets, train our models, and validate their performance. We'll use metrics such as mean absolute error, mean squared error, and R-squared to assess the accuracy of our models. For more complex models, we'll analyze feature importance to understand which variables contribute the most to predicting the price. We'll optimize our models by fine-tuning their hyperparameters to achieve better accuracy and generalization. And drawing final conclusions from our analyses. We'll see how random forests, in particular, offer superior performance in terms of RMSE and R-squared values, especially with imputed data. By the end of this lecture, you'll have a solid understanding of how to build and evaluate robust regression models, ready to tackle real-world data science challenges. Let's get started. Now that we've explored how to compute correlations, it's time to move on to model building. We're going to dive into two algorithms, linear regression and random forest regression. The linear regression is a simple and commonly used algorithm for predictive modeling. It attempts to model the relationship between a dependent variable and one or more independent variables by fitting a linear equation to the observed data. The main goal is to find the best fit line that minimizes the difference between the predicted and actual values, often measured using metrics like root mean squared error and R-squared. Whereas, the random forest regression is a more complex and powerful algorithm that builds multiple decision trees during training and merges them to get a more accurate and stable prediction. It works well with both linear and nonlinear data and can handle large datasets with higher dimensionality. Random forest regression reduces overfitting by averaging the results of many trees and improves predictive accuracy by capturing more complex patterns in the data. Both algorithms are valuable tools in a data scientist's toolkit, with linear regression providing a straightforward and interpretable model, while random forest regression offers higher accuracy and robustness in many cases. Let us now proceed with our actual Capstone project. So for each of these algorithms, we'll be using two different sets of data. The first set is created by removing any rows that have missing values. So, even if just one cell in a row is missing, we'll neglect the entire row. The second data set is where we handle missing values by imputing them. Instead of discarding rows with missing data, we'll use an algorithm to fill in the gaps. We'll apply both the linear regression model and the random forest model to these two sets of data. This way, we can compare how each algorithm performs under different data conditions. Let's start with the first data set where we omit rows with missing values. To do this, we'll use the drop NA command, setting the axis to 0. This means we want to drop any row that contains any number of missing values, whether it's just one cell or all cells in the row. After executing this command, the remaining data is saved into a new variable called cars_neglect. Initially, we had 42,614 records, but after removing all rows with missing values, we're left with 32,751 records. That's roughly about 10,000 records removed. Next, let's consider the columns that are categorical in nature, such as vehicle type, gearbox, and model. The values in these columns are strings, and machine learning algorithms in scikit-learn do not accept columns with string values. To handle the categorical columns, we're going to hot encode them, generating new columns for each category. For instance, if your fuel type has categories like diesel, petrol, CNG, and LPG, we will generate 4 new columns, for instance 4 categories -1. These new columns will be named fuel type _ diesel, fuel type _ petrol, and so on. Each of these new columns will contain binary values, for instance 0 if the category is not present and 1 if it is present. For example, if you have a column called fuel type _ diesel, and if the value in the original column is diesel, then the corresponding cell in fuel type _ diesel will be 1, otherwise, it will be 0. To achieve this, we'll use the get_dummies function from the pandas library and drop the first category to avoid multicollinearity. After running this, you'll see we have a total of 301 columns. We started with 10 columns, and the reason we now have 301 is that several of the original columns, like brand and model, have multiple categories, leading to the creation of many new dummy columns. Before we proceed, let's start by importing some necessary libraries. Here's a quick rundown of the key libraries and functions we'll be using. For instance, we'll import the train, test, and split function from sklearn model selection. This function is essential because we need to split our data into a training set and a test set. The training set will be used to build our model, while the test set will be used to evaluate its performance. Next, we'll import the linear regression function from sklearn linear model. This function will help us build a linear regression model to predict car prices. Then we'll import the random forest regressor from sklearn ensemble. This function will be used to build a random forest regression model, which is another powerful technique for predicting continuous variables like car prices. Lastly, we'll import the mean squared error function from sklearn metrics. This metric will allow us to evaluate the performance of our regression models by calculating the average squared difference between the predicted and actual values. With these imports, we'll be ready to move forward with building and evaluating our models. Let's start by separating our input features and the output feature. We'll call our input features x1, and our output feature will be price, called y1. Here's how we can do it. First of all, let's separate the input and output features. So for the input features, which is x1, we need to drop the price column from cars_neglect and keep the rest. This ensures x1 contains all the features except for the target variable. And for the output feature y1, we'll have only the price column from the data frame. And in our command, we have used in place equals false in the command to ensures that the original data frame cars_neglect remains intact. A new data frame x1 is created, which excludes the price column. This approach provides flexibility and safety in data manipulation, allowing you to perform transformations without altering your original dataset. Now, x1 contains 300 columns, which is all input features, and y1 contains the price column. Next, we will be transforming the price variable, and we will also plot the variable price before and after transforming it into its natural logarithm to visualize the distribution. The reason for this transformation is that the natural logarithm of the price often yields a more normal bell-shaped distribution, which can improve the performance of our regression models. The goal here is to create a new data frame that allows us to compare the original prices of cars before transformation with their logarithmic values, which is after transformation. This code effectively visualizes and compares the distribution of car prices before and after applying a logarithmic transformation. The two histograms provide a clear view of how the data is spread out. The histogram of price shows the original distribution of car prices, which might be skewed with a wide range of values. Histogram of logarithm of price shows the transformed distribution, which is likely to be more normalized and less skewed, making it easier to model and analyze. In these plots, the left histogram shows the distribution of the original price, which is often skewed, and the right histogram shows the distribution of the logarithm of the price, which is more bell-shaped and normal. The bell-shaped distribution on the right suggests that using the logarithm of the price rather than the raw price will likely lead to better regression model performance. Therefore, moving forward, we'll use the natural logarithm of the price against our input features. Finally, we will transform the y1 values to their natural logarithm for our regression models. Now, y1_log contains the transformed price values, and we are ready to use these in our regression models. Next, we will split the data. We will now split the data into training and testing sets. This involves using the train, test, split function, which we've already imported. We'll allocate 70% of the data to the training set and the remaining 30% to the testing set. So, the train, test and split are used to split the data. x1 and y1_log are the input features and the transformed output feature, respectively. The test size equals 0.3 indicates that 30% of the data will be used for testing. And in the last random state equals 3 ensures reproducibility of the split. Let's verify the sizes of our training and testing sets. So, the output confirms that 70% of the data, 22,925 records, is used for training and 30%, 9,826 records, for testing. Before proceeding with advanced models, we'll establish a baseline model. This involves predicting the mean value of the test data as the predicted value for all instances. This sets a benchmark to compare the performance of our future models. This block of code is focused on building a baseline model and evaluating its performance using mean squared error, MSE. Here's a detailed explanation of each step. Baseline pred equals np.mean of y-test. This calculates the mean of the test set's actual values y-test. This mean value will be used as the predicted value for every instance in the test set. This serves as a very simple baseline model for comparison purposes. The baseline MSE uses the mean squared error function to compute the MSE between the actual test values y-test and the predicted values from the baseline model. And the baseline pred, multiplied by length of y-test, creates a list where every element is the mean value, repeated for the length of y-test. This represents the baseline predictions for all test instances. The printed output indicates that the baseline mean squared error is approximately 1.2483. So, the baseline model simply predicts the mean of the test set's actual values for all instances. This results in a straightforward benchmark for evaluating more sophisticated models. The mean squared error, MSE, of the baseline model is 1.2483, which serves as a reference point. Any advanced model should ideally achieve a lower MSE to be considered an improvement over this simplistic approach. By establishing this baseline, we can evaluate how much improvement our regression models will provide compared to simply predicting the mean price for all cars. This sets a useful reference point as we proceed with building linear regression and random forest models. Now, we're going to build a regression and a random forest model. To evaluate their performance, we need a baseline metric. The baseline metric we'll use is the root mean squared error for a simple model where the predicted value is just the mean of the test values. Here's how we'll do it. Step 1, we calculate the mean of test data. In step 2, we replicate the mean value. Since base pred is a single value, we need to replicate it across all 9,866 test records, that is y-test. And finally, in the step 3, we will be calculating the mean squared error. Base MSE equals mean squared error of y-test and base predictions. So, when we talk about mean squared error, it computes the average of the squares of the errors between actual and predicted values. Whereas the root mean squared error takes the square root of the MSE, providing a measure of the average magnitude of the errors in the same units as the target variable. After running the above code, we find that the baseline RMSE is approximately 1.12. This value serves as our benchmark. Any regression model we build should ideally have an RMSE lower than this to be considered effective. By establishing this baseline RMSE of 1.12, we set a standard for our future models. The goal is to build regression models, linear regression and random forest regression, that can predict car prices more accurately, resulting in an RMSE lower than this baseline. This approach ensures we have a quantifiable measure to compare the performance of our advanced models against a simple mean-based prediction. Now, let's proceed with building a linear regression model using the data where we've ignored all missing values. So as a first step, we initialize the linear regression model by creating an instance of the linear regression model with the intercept set to true. Next, we fit the linear regression model using the training data. After training the model, we use it to make predictions on the test set, which is x_test. And then we will calculate the root mean squared error to measure the model's prediction accuracy. From the output we can see that the RMSE for this linear regression model is 0.53, which is a significant improvement from the baseline RMSE of 1.12. This represents roughly a 50% reduction in error. Next, we will compute the R-squared value. Tells us how well the model explains the variability in the target variable. From the output value, the R-squared value is 0.77 for the test set and 0.78 for the training set, indicating that the model explains a good portion of the variability in the data. The close values suggest that the model generalizes well from training to testing data. The linear regression model performs well, with a significant reduction in RMSE from the baseline and a high R-squared value indicating good model fit. Next, we'll run some regression diagnostics to further evaluate the model. Next, we will move on to running regression diagnostics. Helps us understand the model's behavior and identify any potential issues. Like, examining residuals, differences between actual and predicted values, can help identify patterns that indicate issues like heteroscedasticity or nonlinearity. Checking VIF helps identify multicollinearity issues where independent variables are highly correlated. And ensuring residuals are normally distributed validates the assumption of linear regression. We'll explore these diagnostics in the next steps to ensure the robustness of our model before moving on to building the random forest regression model. Let's delve into the residual analysis for our linear regression model. Residuals are the differences between the actual values and the predicted values. They are critical in understanding how well our model performs. So, let us first calculate the residuals as the difference between the actual test values and the predicted values. We will use a scatter plot to visualize the residuals. The x-axis represents the predicted values, while the y-axis represents the residuals. This helps us understand the distribution of errors. This plot is a residual plot, which is a common diagnostic tool used to evaluate the fit of a regression model. So, the x-axis shows the values predicted by the regression model. Y-axis represents the residuals, the differences between the actual values and the predicted values. Each point on the plot represents a residual for a specific predicted value. The scatter of these points gives insights into the model's accuracy and assumptions. The red dashed line that represents the ideal scenario where residuals are 0, meaning the predicted values perfectly match the actual values. The residuals are centered around 0, which is a good sign. It means that, on average, the predictions are not systematically too high or too low. The residuals appear to have a constant spread around 0 across all levels of predicted values. This suggests that the model's variance is constant, which is an important assumption of linear regression. There is no clear pattern in the residuals, like a funnel shape or a curve, which suggests that the model has captured the underlying trend in the data well. If there were patterns, it could indicate that the model is missing some important predictor variables or interactions, or that a nonlinear model might be more appropriate. Some points lie further away from the 0 line, indicating they are outliers. These are instances where the model's predictions differ significantly from the actual values. While some outliers are expected, too many might indicate the model isn't fitting the data well. The residual plot suggests that the regression model has performed well. The residuals are evenly distributed around the zero line without any clear pattern, indicating that the model's assumptions are likely satisfied. The plot helps in confirming that the model has a good fit and that predictions are reliable, though it still might benefit from addressing any identified outliers. Next, we will move on to descriptive statistics of the residuals, which can give us more insights. We expect the mean of the residuals to be close to zero if our model predictions are unbiased. The residuals.describe command provides a summary of the residuals, which are the differences between the actual values and the predicted values from your regression model. Here's a detailed explanation of each statistical metric in the output. The count 9826.00 represents the number of residuals, or observations, in the dataset. In this case, there are 9,826 residuals, which correspond to the number of predictions made by the model. The mean of the residuals is approximately -0.01. This value being very close to zero indicates that, on average, the predictions are very close to the actual values. A mean residual near to zero is desirable as it suggests the model is unbiased in its predictions. The standard deviation measures the spread or variability of the residuals around the mean. A value of 0.53 indicates the typical deviation of the residuals from the mean residual value. Lower values suggest that the residuals are closely clustered around the mean, indicating a better fit. The minimum residual value is -4.78. This indicates that the largest negative error, where the predicted value was much higher than the actual value, is -4.78 units. The first quartile, which is 25th percentile, of the residuals is -0.26. This gives an idea of the distribution of residuals on the lower end. The median, which is 50th percentile, of the residuals is 0.03. The median being close to zero indicates a symmetric distribution of residuals around zero. The third quartile, which is 75th percentile, of the residuals is 0.27. This gives an idea of the distribution of residuals on the higher end. The maximum residual value is 5.42. This indicates that the largest positive error, where the predicted value was much lower than the actual value, is 5.42 units. In summary, the mean residual is very close to zero, and the median residual is also close to zero, indicating that the model's predictions are on average unbiased. The standard deviation of 0.53 suggests that the residuals are reasonably spread around the mean, indicating the model's predictions are consistently close to the actual values. The residuals range from -4.78 to 5.42, showing the model has both underpredicted and overpredicted to some extent, but not excessively. Overall, these statistics suggest that the model has performed well, with residuals that are centered around zero and not too widely spread, indicating accurate predictions. Okay, let us now move to next step, where we'll build a random forest regression model and compare its performance with the linear regression model. And we'll also use data where missing values have been imputed and repeat the model building process to see if imputing missing values improves the model's performance. So, first of all, let's proceed with building a random forest model to predict the car prices. Random forest is an ensemble method that builds multiple decision trees and merges them to get a more accurate and stable prediction. So first, we need to import the random forest regressor from the sklearn.ensemble package. Also, the random forest regressor has several parameters like n estimators, the number of trees in the forest; max depth, the maximum depth of each tree; min sample split, the minimum number of samples required to split an internal node; min samples leaf, the minimum number of samples required to be at a leaf node. The max features are the number of features to consider when looking for the best split. And the random state parameter ensures the same results on every run. So, first we will initialize the random forest model with the specified parameters. Then we will fit the model using the training data. Next, we will use the trained model to make predictions on the test set. Then we calculate the root mean squared error and R-squared value to evaluate the model's performance. So, in the output we can see that the RMSE, commonly used metric to measure the difference between values predicted by a model and the actual values observed. It is the square root of the average of the squared differences between predicted and actual values. In this case, the RMSE for the random forest model is 0.45. So, an RMSE of 0.45 means that, on average, the predictions made by the random forest model are off by 0.45 units from the actual values. This is a relatively small error, indicating that the model is making fairly accurate predictions. The R-squared, a statistical measure that represents the proportion of the variance for the dependent variable, in this case, the car prices, that is explained by the independent variables in the model. It ranges from 0 to 1, where 1 indicates that the model perfectly explains the variance in the data. An R-squared value of 0.84 for the test set means that 84% of the variability in the car prices can be explained by the features used in the random forest model. This is a high R-squared value, suggesting that the model has a strong explanatory power and is performing well on the test data. Similarly, the R-squared value for the training set is 0.88, meaning that 88% of the variability in the car prices can be explained by the features used in the model for the training data. This indicates that the model fits the training data very well. Overall, these metrics suggest that the random forest model is performing very well. The RMSE of 0.45 indicates a relatively small prediction error. The high R-squared values for both the test, 0.84, and train, 0.88, sets indicate that the model has a strong ability to explain the variability in car prices. The slight difference between the train and test R-squared value suggests that the model generalizes well to new, unseen data without overfitting. The random forest model outperforms the linear regression model with a lower RMSE and higher R-squared value. This indicates that the random forest model is better at capturing the underlying patterns in the data and provides more accurate predictions. Next, we will look into the performance of model on the imputed data, where we will perform steps like handle missing values. So, imputing missing values affects the performance of both the linear regression and random forest models. Then we'll compare the models built using omitted data and imputed data to determine the best approach for our car price prediction task. So first we will handle the missing values in our dataset and then build the linear regression and random forest models on this imputed data. The process involves filling missing values with appropriate statistics based on the data type of each column. So, for imputing the missing values, we will use the apply function along with a lambda function to impute missing values. For the columns with float data types, we will fill the missing values with the median. And for columns with object data types like categorical variable, we will fill missing values with the most frequent category. This code efficiently handles missing data in the car's data frame by filling missing values with the median for numerical, float, columns and with the mode for categorical, non-float, columns. This ensures that the dataset is complete and can be used for further analysis or model building without any NaN values. Next, we check for any remaining null values, and we see that none of the variables have missing value now. Next step will be as usual of preparing data for modeling, where first we will convert the categorical variable to the indicator variable using hot encoding method. And after executing the command we have 304 variables as compared 10 in earlier data frame. We will separate the input features and target variable namely x2 in which we will have all other variables excluding price and y2 which will have only price variable. Then we will split the data into training and testing sets and finally we will build the linear regression model. After that first, we're setting up a linear regression model. We call it lin_reg_imputed and then train, or fit, it using our training data, x2_train for the input features and y2_train for the target variable, which is the price. Next, we use this trained model to make predictions on our test data, x2_test. The predictions are stored in y2_pred_lin. After making predictions, we want to see how well our model did. We start by calculating the root mean squared error, RMSE, which gives us an idea of the average difference between the predicted prices and the actual prices. From the output, the RMSE for our linear regression model on the imputed data turns out to be 3812.19. We also calculate the R-squared value, which tells us how well our model explains the variance in the price data. We do this for both the test data and the training data. The R-squared value for the test data is 0.69, and for the training data, it's 0.71. These values indicate that our model is fairly good at predicting prices, as it explains about 69% of the variance in the test data and 71% in the training data. RMSE for linear regression, imputed data 3812.19. This means that, on average, the predictions made by our linear regression model are off by about 3812.19 units of price. R-squared for test, linear regression, imputed data 0.69, this indicates that our model explains 69% of the variance in the price data for the test set. R-squared for train, linear regression, imputed data 0.71, this shows that our model explains 71% of the variance in the price data for the training set. In summary, the linear regression model trained on the imputed data is reasonably good at predicting car prices, with an RMSE of 3812.19 and R-squared values indicating it explains around 69 to 71% of the variance in the data. Now we will move on to building the random forest model. In this part of the code, we're evaluating the performance of our random forest model that was built using data where missing values were imputed, filled in. This command calculates the R-squared value for the test data. The R-squared value indicates how well the model's predictions match the actual test data. A value of 0.84 means that 84% of the variability in the test data is explained by the model. Similarly, this command calculates the R-squared value for the training data. A value of 0.90 means that 90% of the variability in the training data is explained by the model. The RMSE for random forest, imputed data, is 2750.56. This means that the average difference between the predicted and actual values is approximately 2750.56. And the R-squared for test, random forest, imputed data, is 0.84. This indicates that the model explains 84% of the variance in the test data. And finally the R-squared for train, random forest, imputed data, is 0.90. This indicates that the model explains 90% of the variance in the training data. In summary, these commands evaluate the random forest model's performance on both the training and test datasets by calculating and printing the R-squared values. The high R-squared values, 0.84 for test and 0.90 for train, indicate that the model is performing well, explaining a large portion of the variance in both datasets. The RMSE value gives us an idea of the prediction error, with lower values indicating better performance. The comparison of the results across different models and datasets clearly indicates that the random forest model outperforms the linear regression model in both scenarios, omitted and imputed data. For the omitted data, the random forest model has a lower RMSE, 0.45, compared to the linear regression model, 0.5311, and higher R-squared values for both test, 0.84, and train, 0.88, datasets. This indicates better predictive accuracy and generalization capability for the random forest model. For the imputed data, the random forest model also shows superior performance with a significantly lower RMSE, 2750.56, compared to the linear regression model, 3812.19. Additionally, the R-squared values are higher for both test, 0.84, and train, 0.90, datasets in the random forest model, indicating that it captures the data patterns more effectively even after handling missing values through imputation. Overall, the random forest model demonstrates robust performance and better accuracy in predicting the target variable, making it a more reliable choice for this dataset and the given regression task. The linear regression model, while simpler, does not perform as well, especially with the imputed data. With this we come to the end of our Python for Data Science course. We thank you for joining us throughout this course. This course has equipped you with the skills to pre-process data, build and evaluate predictive and classification models, and interpret the results effectively. Whether you're applying these techniques in academia, industry, or personal projects, the knowledge gained here will serve as a strong foundation for your future endeavors in data science and machine learning. We hope this course has been useful to you, providing you with practical skills and a deeper understanding of predictive modeling. Keep experimenting, learning, and pushing the boundaries of what you can achieve with data science. And at the end we request you to like, share and subscribe to our channel and stay tuned for upcoming lectures.